Locating octahedral and tetrahedral voids. So first we will see how we can locate octahedral voids in CCP or FCC crystal lattice. Okay, so here we have this unit cell which is divided into 8 small cubes. So these 8 small cubes, don't think that they are individual unit cell, but this total, here we have only one unit cell, but we have, for our convenience, we have divided in 8 small cubes. So that is clear from this picture. 1, 2, 3, 4, then 5, 6, 7, 8. Now the body center of the cube, that is, if we focus on this part, there is no atom present. So this is the body center. Suppose it is C. Okay, so C is basically not occupied. So C is basically not occupied, but it is surrounded by 6 atoms on face centers. So these 6 atoms are 1, 2, 3, 4, 5, 6. So if you join all these lines, that is joining all these lines, face centers creates a octahedral. So the shape that we have obtained here, which is drawn by bold black line, this is actually an octahedral shape. So in the center we are getting one octahedral void. So this unit cell has one octahedral void at the body center of the cube. Fine. Next we will see that this is not the only octahedral void that is possible in FCC. Some other octahedral voids are also possible. So now what we have done, so there is one octahedral void at the center of edge of 12 edges. So in this unit cell there are total 12 edges. This is one edge, 2, 1, 2, then 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12. So these are the 12 edges. Now at each edge, that is, if we consider the center of each edge of these 12 edges, it is surrounded by 6 atoms. And here we can see we have considered this edge. So surrounding this edge, there is one octahedral void at the center of this edge, and surrounding it there are total 6 atoms. Now see, among these 6 atoms, 2 atoms are not in the unit cell. That is, 2 atoms that belongs to adjacent unit cell. So which are these 2 atoms? This one and this one. So this is not part of the unit cell, right? But the other 4 atoms, that is this one, 2, then 3 and 4. So I have given here vertical line so that you can differentiate between these 2. So this vertical line that I have drawn beside the atom, these 4 atoms are part of the unit cell. So 4 belonging to same unit cell and 3 belonging to 2 adjacent unit cells. Now each cell of the each edge of the cube, if we consider, then it is actually shared between 4 adjacent unit cells. So just focus on any of this edge. So each edge, it is shared between 4 adjacent unit cells. So here we have, if you focus on this edge, then we can see here only one unit cell, but basically on other side there are 3 more unit cells. So it is, this edge is part of basically total 4 unit cells. That means here this octahedron, that is not just part of this cell, but it is also part of other 3 unit cells. Okay, so that is why each edge of the cube and octahedral void are shared between total 4 adjacent unit cells. Okay, so here in the first case we have obtained one octahedral void which is at the center, and here we are getting 12 octahedral voids, but it is shared among 4. So here we are obtaining one void which is completely inside the unit cell. So it is not shared with other unit cell. But in the second case, there are total 12 octahedral voids possible, but it is shared among 4 unit cells. So if we want to know what is the contribution only in this unit cell, so it will be should be multiplied by 1 by 4. So here the contribution of this void, that is the part of this void that is included only in this unit cell, this value will be 3. Okay, so this is 3. Now 1 and 3 total number of voids, that will be 4. Now see, in previous class we have seen that total number of atoms that is in the atom, what is the total number of atoms, that is always equal to the number of octahedral voids. Now in FCC there is actually total number of atoms 4, and how we can obtain this, that we will see today. But remember, number of octahedral voids, that is always equal to the total number of atoms that is present in the unit cell. In case of FCC, this is also 4. Next we will see tetrahedral voids in FCC. Again we have taken the same unit cell and it is divided into 8 small cubes, so that this is for our convenience, fine. And in all these small cubes, each small cube has 4 atoms. Okay, so if we consider this cube, so I am just highlighting the one part among 8. Okay, so this is one of the 8 parts. So in this particular portion, there is total number of atoms 1, 2, 3 and 4. Now if you join all these lines, when joined to each other, they make a regular tetrahedron. So total number of tetrahedral voids will be 8, because there are total 8 small cubes. We have divided the unit cell in 8 small cubes. So in one small cube there is one tetrahedral void. So 8 small cube means 8 tetrahedral void. Okay. Now as I have said that in CCP or FCC structure there are total number of atoms which is 4 per unit cell. So here we are getting total 8 tetrahedral void. That means now it is double. Okay. So number of atoms, if it is n per unit cell, then octahedral void will be n and tetrahedral void will be 2n. Remember this. Okay, so when you will solve problem, then this formula, it will help us. Next you will see that number of voids filled, and from that how we can determine the chemical formula. Okay, so if the solid in which close packing exists is an ionic solid, what will happen? Then these voids are very important. Remember, solids may be different types that we have already seen, but if it is ionic solid, obviously there will be ions. Now these voids play a very important role. And how it plays the important role? The bigger ions, obviously if you consider anion and cation, anions are always bigger in size compared to cations. So the bigger ions from the close packed structure, usually anions, and the smaller ions, that is usually in most of the cases it is the cations. Both of them, only the cations, they occupy voids, but the anions, they reside at the close packed structure. That means where we have the lattice points in the crystal structure, these points are taken by anions, and cations are always occupying the voids. Fine. So now there are 2 types of voids, tetrahedral void and octahedral void, and we know that tetrahedral voids are always smaller in size compared to octahedral void. So if the cation is small enough, because cation may be small or it may be big, if it is small, then tetrahedral voids will be occupied, and if it is bigger, then octahedral voids will be occupied. So it depends. Next, here you can see we have NaCl crystal lattice. Here anion is chlorine and cation is sodium. Now sodium, that will be in the voids. Now you can see here these cations, that is all the red dot, they are actually at the octahedral void. So just we have seen the position of the octahedral void. So they remain at the edge center. So you can see 1, 2, 3, 4, 5, 6, 7, 8, then 9, 10, 11, 12. So total 12 octahedral void, and in the center also there is one. So there is all these octahedral voids, that is they are occupied by sodium plus, that is cation. So sodium plus, it is bigger in size, that is why they are in the octahedral voids, not in the tetrahedral voids. And the actual lattice points are all these blue dots. Okay, so we know that in FCC there is at 8 corner there will be total 8 atoms, and also in the face there will be atoms, face center. Okay, so here you can see that in the corner we have all these anions. So this is the 8 corner, and also in the middle of each faces 1, 2, 3, 4, 5, 6. So total 6 faces. So total number of atoms 8 at corner and 6 at faces, that is 14. So Cl minus, that is occupying at the lattice point. So anions, as we have said here, the bigger ions, that is anions, they form the closed pack structure. So they reside at these points where actual lattice points are present. But the smaller ions, that is cations, they remain in the voids. Now depending on their size, they may occupy tetrahedral void or they may occupy octahedral void. Okay. However, all octahedral and tetrahedral voids are not occupied. So it is not necessary that all octahedral and tetrahedral voids, it should be occupied. No, that is not necessary. In a given compound, the number of voids occupied, that depends on the chemical formula of the compound. Okay. So if it depends on the chemical formula, that means if we know the number of total octahedral voids and total tetrahedral voids occupied, then we can determine the chemical formula of the compound, because these two are related to each other. Okay, so we will see how we can do so. Here we have a problem. What is the formula of a compound in which the element Y forms CCP lattice and atom of X occupy 1/3 of tetrahedral voids? So as we have said that anions, mostly they reside in the lattice point. So here Y is actually anion, and the atom X, that occupy 1/3 of the tetrahedral void. So here cation is basically X, but that is not important, because here our purpose is to find the formula, chemical formula from this information. Okay, so first of all, CCP lattice. CCP means it is also, you can say, FCC. CCP, FCC, both are fine. So here number of atoms, suppose number of atoms N. Okay, so if that is the case, then number of tetrahedral voids will be 2n, because we have already seen it is always the double. If it is octahedral, it is same number as the number of atoms in the lattice, but if it is tetrahedral void, it will be double. Okay, now 1/3 of the tetrahedral voids are occupied. So all the tetrahedral voids are not occupied, only 1/3 is occupied. So X is present in 1/3 of 2n. Okay, so number of y will be n and number of x will be 2n by 3. So the ratio of x and y, it will be 2n by 3 is to n. Now how we can change it? 2n is to 3n. Just multiply both, that is, as it is a ratio, if you multiply the numerator and denominator by 3 then it will be 2n and the second one will be 3n. So we have multiplied both by 3. So now the nn will be cancelled. So the form ratio of x and y, it will be 2 is to 3. So the formula will be x2 y3, right? The next question, a compound forms hexagonal close packed structure. What is the total number of voids in 0.5 mole of it? How many of these are tetrahedral voids? So it is hexagonal close packed structure. So in HCP structure also, just like FCC, here the total number of tetrahedral voids is 2n and total number of octahedral voids will be n. That is, their amount is always, that is tetrahedral voids, octahedral voids, it is 1 is to 2. So the ratio is octahedral void is to tetrahedral void, it is always 1 is to 2. So if total number of octahedral voids is n, then tetrahedral voids number will be 2n. Okay, so here total number of atoms in 0.5 mole, first we will find that. So we know that in 1 mole there is Avogadro number of atoms. So 1 mole will contain 6.0, it is, if we consider 6 into 10 to the power 23, that is also fine. So 6 into 10 to the power 23. For the convenience of calculation, I have considered it 6 into 10 to the power 23. So 0.5 mole, it will contain 6 into 10 to the power 23 divided by 1 multiplied by 0.5. So this will be 3 into 10 to the power 23. So this is the total number of atoms. So here total number of atoms, that will always be equal to the octahedral voids. So here octahedral void is number of octahedral void is also 3 into 10 to the power 23. And how many of these are tetrahedral voids? Okay, so this is the number of octahedral void. Number of tetrahedral void will be double, so it will be 6 into 10 to the power 23. And here we have two questions. One is how many of these tetrahedral voids and what is the total number of voids. So total number of voids will be, we will add these two figures. So number of tetrahedral void is 6 into 10 to the power 23. This is the second answer, okay, this one. And total voids will be 3 into 10 to the power 23 plus 6 into 10 to the power 23. So it will be 9 into 10 to the power 23. So this is the total number of atoms, total number of voids, and out of it only 6 into 10 to the power 23, these are tetrahedral voids. Okay, so and octahedral voids, though it is not asked in the question, but octahedral voids also we require because we have to find total voids. So that's why we have added octahedral void and tetrahedral void. Next we will see how we can find number of atoms in a unit cell. So until now what I have said, that in FCC total number of atoms 4. But how we can obtain that, now we will see that. But before going to that point, what we have to see that how the atoms are shared between other unit cell. Okay, so we cannot simply count all the atoms or ions that form the unit cell. So if someone is asking that what is the total number of atoms present in unit cell, then it is not that we simply count the number of atoms and we say that this is the total number of atoms present in unit cell. No, that is not the case. Now why it is so? Because many of the particles, they may be part of more than one unit cell. So as you have already seen, when we have determined the octahedral voids, then we have considered that it is shared among 4 unit cell. That means its contribution to one unit cell will be only 1/4. Okay, so similarly here also, when we will count the total number of atoms or ions that is present in the lattice point of the unit cell, what is the contribution of that atom? Now suppose the particle is present at face center. So this is one of the face and the particle is present in the center. Now particle is actually sphere. Now here you can see this part which is protruding here, this is actually part of the another unit cell, and the part which is the contribution for this blue unit cell, that is actually inside. Okay, so half of it is outside and this half is not part of this unit cell. So for each face center atom or ion, its contribution will be half. So for face center, what we will do, we will count total number of atoms that are present in the face center, and then we will multiply it by half, because only half is included in this unit cell, other half is not included here. Okay, so this is for the particle at face center, it is shared among 2 unit cell. Another possibility, particle, it may present at corner also. So particle present at corner, shared among 8 unit cell. So here you can see total number of unit cell, here we have actually 7, and in this vacant position also there is another unit cell present. But so that we can understand, we can see this 1/8 part of this particle is actually the contributed part towards this unit cell. So when the particle is present at the corner of the unit cell, it is actually shared among 8 unit cell. So if there are total n number of particles at corner, so it will be n into 1/8. So this is the amount which is actually included in this unit cell. So total number of particles, if it is n, it will be multiplied by 1/8 because it is shared among 8 unit cell. So its contribution will be n/8, and in the previous case it will be n into half. Particle at the body center. Now particle, when it is present at, sorry, it is not body center, it is edge center, because when it is present in body center, that is actually the 4th possibility. Suppose we have this unit cell and in the body center there is one particle present. Now see, this is completely inside the unit cell, so its contribution will be full contribution. So here it will be simply n multiplied by 1, that is n. Okay, now if the particle is at edge center, so this is edge, and here we have 3 unit cell, red, green and blue, and here also this portion is vacant, but here another unit cell is actually present, but that is not shown here, so that we can understand that here the contribution for this edge center particle, its contribution for one unit cell, it will be 1/4. So if there are total number of edge center particles is n, its contribution for one unit cell, it will be n into 1 by 4. Okay, so here we have seen total 4 possibilities. Particle as face center, contribution half. Particle at corner, contribution 1/8. Particle at edge center, contribution 1/4. And particle at body center, full contribution. Okay. So here we have, in this table we have all the information that we have seen. Okay, corner 1/8, edge 1/4, face center 1 by 2, and body center full contribution. So these are the types of lattice points, that is the type of position of lattice points in the unit cell: corner, edge, face center, body center, and the corresponding contribution towards the unit cell. Now we will take different types of unit cell and we will find out what is the total number of atoms present in it. So primitive cubic unit cell, this is the simplest unit cell that is possible. So in this primitive cubic unit cell, we have atoms only at the corner. So this is one type of picture, and you can see here another picture. Actually this is the real picture, because here it is not that you can see all these lines. Fine, they are very large in size, so it is actually the space filling model, this one, and this is the actual model, but we draw it in this way so that we can understand it very easily and we can see the square, because in this picture you cannot see the square. Okay, here the atoms are only located on the corners, so total 8 corners. Each atom located on the corner, we have already seen its contribution is 1/8. So if there are total number of particle is 8, so 1 by 8, so this will be 1. Now if you look at this right hand side picture, here you can actually understand that this is the part, because here we do not have the full sphere, we have only 1/8 part of each sphere. Okay, so this is one part, 2, then 3, 4, this is 5. Here we have one which we cannot see because it is away from us, then these 2. Okay, so total 8 atoms. So this is the 1/8 atom at the 8 corner, this is the 1/8 part. Okay, and this picture is basically actual portion of atoms that belong to one unit cell. Okay, so here number of atoms present in primitive cubic unit cell is 1. Next type is body centered cubic unit cell. Now in body centered cubic, it is just like primitive cubic unit cell, only difference is now in the body center we have another particle, so it is in different color. And this is the space filling model, where these lines are not present but spheres are very large in size. Okay, so in body centered unit cell, for these 8 corner atoms, their contribution will be same as we have seen in the previous case, 1. And at the body center, this has full contribution. Okay, so that is why it will be 1, as if it is, you can say 1 into 1. So this is 1. So total number of atoms, 8 atoms are 8 corner and 1 atom present at the center. So this 1 atom full contribution, and for this 8 atom only 1/8 contribution. So total number of atoms will be 1 plus 1, that is 2. Again the picture, but now what is the difference? Now we have at the center another particle. Okay, actual portion of atoms belonging to one unit cell for body centered cubic unit cell type. So here number of atoms per unit cell for BCC is 2. Face center cubic unit cell. So just like primitive cubic unit cell, that is the simplest, we have 4 atoms at 4 corner. All these pink balls, and there are also in the face center there is atoms present, which are the blue one. Now in a cube obviously there will be total 6 faces, so total 6 face centered atoms. So 1 2 3 4 5 6. Now look at this picture, that is the actual portion of atoms belonging to one unit cell. Here, just like the primitive cubic unit cell, 1/8 atom at 8 corners, and for face center we know it's when any particle is present at the face, it is divided between 2 unit cell, so its contribution will be half. Okay, so 8 into 1/8, 1, and 6 for 6 faces, their contribution is half, so it will be 3. Now add these two numbers, so total number of atoms in FCC is 4. Okay, so this we have discussed in previous slide, but now we know what is the actual reason that total number of atoms in FCC unit cell, it is 4. Okay, so here we have in the table all the values that we have obtained. Simple cubic, it is 1. For body centered cubic, it is 2. For face centered cubic, it is 4. And end centered cubic, actually these are less common, so that is why picture is not shown. But if we draw the picture of end centered, so at 4 corners there will be actually 8 corners, 4, and lower part 4. And what is the difference now? In the end center, any 2 opposite faces, there will be 2 more particles. So the contribution for the red one, it will be 8 into 1/8, and contribution for the blue one, it is total number is 2 and contribution is half. So we are getting 1. This is also 1. Just add these 2. This will be 2. So for end center cubic, the value is 2, just like body center cubic. Okay, so in this way we can find number of atoms in a unit cell. Now we have a question here. A compound MpX3, this is the formula. It has CCP arrangement or FCC, both are same. CCP arrangement of X, fine, and its unit cell, the picture is also given. So X is basically present at the lattice points. X is round shape and M is square shape. So X is present at 8 corner and also 6 face. 1 face, 2nd face, 3rd face, 4th face, 5th face, 6th face. Fine. So X atoms are basically present at corners as well as face center. So we will find here the empirical formula, but before that we have to know what is their contribution. So number of X ions, it will be present per lattice. Obviously it is the anion, that is why here it is X minus. Okay, because anions, that is the bigger ions, they always occupy the lattice points. Okay, so 1/8 of the number of ions present at corner of the cube. Now at corner there is 8, so 1/8 of 8, and half of number of ions present at face center. Now total face center number of atoms 6, so half of 6, it will be 3 and it will be 1. So its contribution is 4. Now next we will consider M, because M is present from the picture. You can understand M is present. If I use different color, so M is present at these 2 edge, another 2 edge, and at the body center. So for the body center, its contribution will be full contribution. M plus ions are present at 4 H center and 1 at body center. So for this body center, its contribution will be full, and for this H center, we know any particle present at H center, they are shared among 4 unit cells. So total H center is 4, so it will be 1/4 of 4. Okay, so 1/4 of number of ions present at H center of the cube, 1/4 of 4, and number of ions present at body center, its full contribution. So now it is 2. So what should be the formula? The ratio of M and X, it will be 2 for M, 4 for X, that is anion. So if we simplify it, it will be 1:2. So the formula will be MX2. So correct option is option 2. So here it can also ask that what is the value of P and Q. So here P is 1 and Q is 2. Okay, so this is the formula, empirical formula. Okay, so from this problem we can understand that how, if we know the positions of the anions and cations, whether they are occupying tetrahedral void or octahedral void, here actually direct picture is given. So that is also possible. When you will get problem, you can get picture, or it may be simply written that how many tetrahedral or octahedral voids are occupied and the lattice points where the anions are present. Okay, and from this information we can find out the empirical formula. Fine. We have another problem here. A solid has a structure in which W atoms are located at the corners of the cube. W atoms are located at the corners of the cube. W means tungsten. Fine. Oxygen atoms are located at the center of the edges, edge center, and sodium atoms are present at the center of the cube. So we have to find the formula of the compound. So tungsten, it is present at 8 corners because there are total 8 corners possible. So its contribution will be 8 into 1/8, that is 1. Oxygen atoms are present at edge center. Now total edge center is 12, and when any particle is present at edge center, it is shared among 4 units. So its contribution will be 12 into 1/4, that is 3. Atoms of sodium are present at the center, so it will have full contribution. So it is 1. So the ratio of W, oxygen and sodium, this is 1:3:1. So what will be the formula? Formula will be NaWO3. Here options are not given, but if options are given, we can choose that. Fine. So this is the formula of the compound which we have obtained from this simplest ratio. Next we will study packing efficiency. So packing efficiency, first of all we have to know what it means. So it is a percentage of total space that is filled by particle, because we know in the unit cell there are voids as well as there are particles. So actual space that is filled, we have to find out that percentage, and it is also known as packing efficiency. So how to find out packing efficiency? It is Z. Now what is Z? Z is the number of atoms present in unit cell. So we have already seen that for BCC it is 2, for FCC it is 4. We already have seen that how to calculate. So you have to put that number Z into volume of one atom. So if radius of the atom is given, we can easily find the volume of one atom or particle, and divided by volume of the cubic unit cell. So we have to know the edge length of the unit cell, and if edge length is A, that means volume will be A cube, and volume of one atom, the formula for volume of sphere is 4/3 pi r cube. So that is written here. This is the volume of one particle. So volume of one particle is this. So we are multiplying it with Z. So volume of total atoms. Basically this is equal to volume of all atoms that are present in one unit cell divided by volume of the unit cell. And if we multiply it with 100, it will give the percentage of the space which is occupied by the particles, and this is also known as packing efficiency. So now we will calculate the packing efficiency for simple cubic lattice. So here we have a picture which is for simple cubic lattice, and total number of atoms you can see 1, 2, 3, 4, 5, 6, 7, 8. Now we will focus only these two spheres. For calculation we will consider these two. So here if I join the center of this sphere H and A, this is basically the edge length of the cube, right? So this is actually A, this distance is A. Now this distance is also 2r, because if radius of one atom, if it is r, this is the radius, this is another radius, this is also r. So now we can write that 2r is equal to A cube. Sorry, 2r is equal to A, not cube. 2r is equal to A. Okay, so volume of unit cell will be volume of unit cell is A cube, that means it is 2r cube or 8r cube. Now we have to find volume of one particle or one atom. So this will be 4/3 pi r cube, and there are total number of atoms possible in simple cubic lattice, that is Z value is here 1. Okay, so packing efficiency will be packing efficiency, Z is 1, so 1 into volume of one atom divided by volume of the unit cell, so multiplied by 100. So it will be 4/3 pi r cube multiplied by 1/r cube. So r cube will be cancelled. This is 2. So this is basically pi by 600. So pi by 600, if we calculate it, this will be equal to 52%. So here packing efficiency for simple cubic lattice is 52%. Okay, so in this way we can also calculate packing efficiency for FCC and BCC. Here we have body centered cubic unit cell. So in body centered cubic unit cell, if you look at this picture, some atoms are here shown. So corner atoms G, H, B, C, D, E and also F. So these 4 are the corner atoms. Now A is also corner atom and C is at the body center. So for body center, what we have done, we have joined the middle point center of E sphere, the center of A sphere. So when you are joining these two lines, basically it is going through the center of the body centered atom also. Okay, so this length, this is R, and this portion is R. Sorry, it is 2R because it is a full, it is not just radius, it is a total length. Okay, so 2 into radius, and this part is another R. So this body diagonal means it is not on the face, it is inside the body. This diagonal, this length is actually 2R plus R plus R, that means it is 4R. Now how to do the calculation? Here we have considered the triangle EFD. So EFD, if we consider, that is this triangle. Let me use another color. So this is the angle EFD. So in this angle, suppose DF is B. DF is B and ED equal to EF, because this is one edge length and this is another edge length. So this is A, this is also A. Fine. Now we can say that B square, that is this distance ED, that is equal to A square plus A square. That is, you can also write it as ED square, which is B, that is equal to, sorry, it is DF square. DF square, which is B, that is equal to ED square and EF square. So this is B, this is A, this is A. So B square equal to 2A square. Next we will consider another triangle, which is AFD. Now what is AFD? AFD is this one. Now for this triangle, we can write that AF is actually C. It is mentioned here. And AFD is B, that we have already calculated. And AD is A. So this is A, AD. Now C square will be equal to A square plus B square. Now B square we already calculated, it is equal to 2A square. So in place of B square, now we will write 2A square. So it will be 3A square. Fine. So C square equal to 3A square, that means C will be equal to root 3A. So C is the body diagonal. And as we have seen there, that it is equal to 2R plus R plus R, that is 4R. 2R plus R, which is 4R. Now C, in place of C, if we write 4R, it will be 4R equal to root 3 by A. Now we are obtaining the relationship between R and A. So R is equal to root 3A by 4. Root 3A divided by 4. Or we can say A equal to 4R by root 3. Okay. So volume of one unit cell, because we are basically, our purpose is to find out packing efficiency. But for that we should know what is the volume of unit cell. So volume of unit cell is A3. Now we will put the value of A, which is 4R by root 3. So it will be 4R by root 3 to the power cube. And in BCC we have already calculated that total number of sphere or atom or particle, whatever you want to say, it is 2. So volume of 2 sphere will be 2 into 4 by 3 pi r. So packing efficiency, here Z is 2, volume of one sphere is 4 by 3 pi r cube divided by A cube. Now A cube means 4R by root 3 cube. Okay, and that is multiplied by 100. So if we simplify it, it will be 8 by 3 pi r cube multiplied by, here we will have 4 cube. 4 cube means 64 r cube, and root 3 its cube, so it will be 3 root 3. So 64, it will be 8, r3 will be cancelled, 3 will be cancelled. So finally we are getting root 3 pi divided by 8 multiplied by 100. Okay, so this will be equal to root 3 pi divided by 8. If you do the calculation, you will find 68%. So here packing efficiency is 68%. In the previous case, it is a simple lattice we have seen, it is 52%, here it is 68%. Face centered, or we can also say HCP or CCP. So here total number of sphere is 4. Okay, now again we have taken here this unit cell, and now we will consider this face diagonal. So in face diagonal, we know in FCC, in the face center also there is one particle, and at corner already there are 2. So if we join the center of A and the center of C, the line will go through the center of B also. Okay, now this distance is 2r, this distance is r, and this is also r. So total this body face diagonal, that will be 4r. Now come to this side, volume of 4 spheres, it will be 4 into 4 by 3 pi r cube. 4 into 4 by 3 pi r cube. Now AD is the face diagonal. Face diagonal, it is equal to 4 times of the radius of sphere, it is C, not D. So AC will be equal to 4r, you can also write it as 2r plus r plus r. Now if we consider the triangle ACD, this is actually right angle triangle, because this angle is 90 degree. So for this triangle, what we can write, the face diagonal, that is AC, that is equal to, AC is AC square, that is equal to AD square and DC square. So this length and this length, you have to take the summation of their square, which will be equal to the square of AC. So AC square is equal to AD square plus DC square. Now AD is A, because A is the edge length. So this length is A, this length DC is also A. So we will put in place of AD and DC AA. So AC square will be equal to root 2A. Now AC, what we have written here, it is equal to 4r. Sorry, it will be 2a square. So AC is equal to root over 2a square, that means root 2a. Now AC is also equal to 4r, so we can write 4r equal to root 2a, that means A will be equal to 4r divided by root 2. Okay, so volume of the cube will be, you can also write it as 2 root 2 divided by root 2 r. So if you cancel it, it will be 2 root 2 r. So volume of the cube is basically A cube, and as A is equal to 2 root 2 r, so 2 root 2 r is r cube to the power cube, and volume of 4 spheres we have already calculated. So packing efficiency will be, Z value is 4, volume of one particle is 4 by 3 into pi r cube, and that will be divided by 2 root 2 r whole cube. So this is, if we simplify it, it will be 16 by 3 pi r cube multiplied by 1 by 8 into 2 root 2 r cube multiplied by 100. So r cube will be cancelled and it will be 2. So 2 will be cancelled. So what we are getting finally, if I write it here, it will be pi by 3 root 2. And if you do the calculation, it will be 74%. Now look at this table. Here we have all the values together. For simple it is 52%. Coordination number is also given for your convenience. Body centered, the packing efficiency is 68%, and for face centered we have just calculated it is 74%. So one question may be there, that among these three types, in which case packing efficiency is maximum and in which case it is minimum. So in face centered, the packing efficiency is maximum, which is 74%. In case of simple cubic lattice, it is 52%. So its packing efficiency is minimum. And you can also correlate it with the coordination number, because when packing efficiency is very high, obviously coordination number, that is number of atoms surrounding the central atom, that is the coordination number. So high packing efficiency, that is associated with high coordination number, and minimum packing efficiency, that is also correlated with minimum coordination number. So when the surrounding number of particles is less, that means packing is not very good. And if surrounding the particles, if we count the surrounding particles, the coordination number, if it is very high, that means the vacant space, that is void amount, is very less. That means the spaces which are occupied, that is very high. That is why here it is 74%. Okay, so in this way we can find packing efficiency. Now for this there is a question which is related to packing efficiency. Here the packing efficiency of two-dimensional square unit cell. Now see, this is not cube, it is not three-dimensional, it is two-dimensional. It is two-dimensional square unit cell, and here we have 4 different options for packing efficiency. And if you look at the picture is given with the question. Okay, so first of all, what we will do, we will find out total number of atoms per unit cell. So total number of atoms per unit cell, it is for these 4 cornered atoms, its contribution is actually, it is shared among 4 other unit cells. Just extend this line. So there is 1, 2, 3 more unit cells. So this atom is shared among 4 unit cells. So that is why 1 by 4 of 4, and the central one, that is full contribution. So total number of atoms is 2. It is actually the Z value. Radius of the atom we will consider small r, and here the value of SR, QR, that is all the edge, PQ and SP, all are actually L, that is the edge length is L, and QS, that will be equal to 4R. Now how it is so? Because here it is simply written as atoms, so that the picture is simple, but actually they are sphere, right? So if you write it in this way, though my drawing is not proper, but I hope you will understand it, that if we draw this, then this distance is R, this distance is 2R, and again R. So it will be 4R, 2R plus R plus R. So this is the diagonal. So now we know the diagonal value QS, SQ. QS is 4R, and total number of atoms Z, radius of the atom R. Now we will consider the triangle SQR. So here the triangle SQR, what we can write? SR square, that is this side, plus QR square, that is equal to SQ square. That means L square plus L square, that is equal to 4R square, because QS is 4R. Okay, so from this relation we can find that 4R square means what? 2L square, that is equal to 16R square. Fine. So R will be equal to, R square is 2 by 16 L square, 1 by 8. So R will be equal to root over L square by 8, and that is root L, sorry, it is not root L, it is L by 2 root 2. And that is also written here. Okay. Now we will find the packing efficiency. So packing efficiency, it will be total number of atoms, that is Z. Our Z is 2. So 2 into volume of one particle. So it will be 4 by 3 pi. Sorry, the formula is not like that, because it is two-dimensional area. It is not volume, it is actually area, because now we have two-dimensional square. So you should always read the question carefully, what it is actually asking. So the formula now will be different. So here area of atoms, area of one atom, divided by area of unit cell, multiplied by 100. So area formula is pi r square. This formula is pi r square. So this is equal to 2 into L by 2 root 2 square into pi, and area of unit cell, that is we have to put the value of L, simply L square, because edge length is L, multiplied by 100. So if you do the calculation, it will be basically pi by 4 into 100, and that is equal to 78.5%. So it is matching with which option? It is matching with last option. Okay, so here packing efficiency, this question is very important, because until now what we have seen, how to calculate packing efficiency in 3-dimensional space, but it is 2-dimensional square unit cell. But whatever we are doing, that is the rules that we are following, this is same analog of that we have done in case of 3-dimensional space, but here it is 2-dimensional space. So that is why now the formula is different. Instead of volume, now we will consider area. Okay.